Welcome to the American Shoulder and Elbow Surgeons Podcast. I'm your host, Peter Chalmers, a shoulder and elbow surgeon at the University of Utah in Salt Lake City, and I'm joined today by my co-host, Rachel Frank, a sports and shoulder surgeon at the University of Colorado in Denver. Rachel, how are you?
Doing well, thanks, Pete. How are you today?
Oh, I'm doing great. Before we get started, I should mention the views expressed in this podcast do not necessarily reflect the views of the American Shoulder and Elbow Surgeons Society, the University of Utah, the University of Colorado, or the institutions of any of our guests. Today, we have a real treat for you. We're going to talk about basic science research, and we've got two absolute superstars, but with very different backgrounds and who focused on very different areas. So first, we have Dr. Scott Rodeo, Chief Emeritus of Sports at ASES. Scott, welcome to the podcast.
Thank you. Thanks for having me. Glad to be here.
Well, we're really glad you could be with us. Next, we have Dr. Thay Lee, who is the Chief Scientist at the Congress Medical Foundation and the Vice Chair Emeritus at UC Irvine. Thay, welcome to the podcast.
Thank you. It's very happy to be here.
So I wanted to start by asking both of you how you first became interested kind of in basic science orthopedic research. So Scott, tell us first, how did you get into this area of research?
My interest was always kind of in sports injuries, and so I kind of gravitated toward tendons, ligaments, cartilage, things like that. I remember, what got me interested in, I was a third or fourth year medical student, 1988 paper from Steve Arnoxley and Russ Warren, where they evaluated a fibrin clot to heal for meniscus healing. And that just struck me as a cool area, one of the earlier, papers in the kind of biology of soft tissue repair. And that's what kind of sparked my interest. And I had interest in studying soft tissue injury, having had my own injuries as an athlete. I came during my residency to realize all really the deficiencies in our treatment. So I kind of looked at almost a glass half full, if you will, or half empty, I should say, in a negative way. And by that, I mean, I realized all, the limitations in our treatments for cartilage, for meniscus, for ligament, for tendon. And that's really sparked my interest in wanting to understand more about the underlying pathophysiology of these tissues and how we can ultimately use that information to figure out how to treat these things better.
What about you, Thay? How did you first get into the area of research you've so dominated for the past 20 years?
Okay, the way I got into it is a little different than most of the surgeons, obviously. I'm a scientist in a clinical field. I'm a mechanical engineer by training. And while I was an undergrad, when I first saw an orthopedic implant, I thought that was the coolest thing. The engineering that goes in there, as well as the longevity that goes in. So I got interested in it, and I got to study with Dr. Savio Wu, who is one of the pioneers in biomechanics, and kind of went through and learned research methods through him. And through that process, while going through graduate school, I thought to myself that this is the only job that you get to do something no one's ever done, and you get paid for it. So I kind of gravitated towards what I was interested in, which was more of joint mechanics as well as joint prosthesis, and just started to develop my research interest going from there. But more importantly, I think through my experience, the most important factor on my productivity is surgeon partners. So I was very fortunate enough to work with very motivated surgeons who are thinkers, and we're able to solve problems that came up. And as far as topics went, it was actually very simple. I tell my residents and fellows this all the time, that they can't get research ideas. Basically, all the research ideas come from operating rooms or while treating a patient. And there's no way that we already have answers to everything. And that's where all the questions come from. And there's plenty of them. And we just try to utilize all the, technology that we have trying to solve it.
Now, both of you have made some incredibly large contributions to our field, not just for orthopedics, but I think that each of you and your works have inspired medicine in general. Now, it's interview season for residents and fellows, and often residents and fellows get asked, what's your most favorite study? What's your study that you're proudest of? And Pete and I want to ask each of you this, given the volume of work that you've contributed and the relevance of the work you've contributed. So, Scott, let's start with you. What's the paper or series of papers that you are most proud of?
Rachel, it's a good question. I go back. One of my fundamental interests has been in interfaces, healing between soft tissue and bone, and it really goes back to my first work I did with Steve Arnoxy. And this is another point I would make, and Thay kind of brought this out: is collaborations and collaborators and really role models. But so I started with Steve Arnoxy when I was a resident here at HSS, and Steve being obviously a kind of major figure and father of soft tissue research. So we did a study looking at the soft healing of a tendon graft in a bone tunnel, and that's just one particular paper. We published that as a resident, but it sparked my interest in continuing this area of research that I really continued honestly to this day. And to your question about sort of a series of papers, that's where we've kind of continued to study that area. And this is, I think, a good lesson for all of us and our younger trainees is pick an area and really just delve into it and follow that area over time, because each study you do brings up 3 more questions. And so we've followed that area and studied in particular the role of mechanical loading and how that affects biology. We've used that line of investigation to study the role of cytokines and now the signaling molecules. And the techniques we have available now didn't exist 20 years ago, and the ability to use transgenic models and high resolution imaging in our animals and RNA-seq and multi-parameter flow cytometry, these high dimensional data analysis techniques that allowed us to continue to study, frankly, the same thing I was studying in the early 1990s, but at a much higher resolution. So that's kind of what sparked my interest. But it really goes back to our first work in tendon healing in the bone tunnel.
And Thay, how about you? What is the series of papers or the single paper that you're most proud of when you say, this is, if I could be known for anything, or this is what I'm most satisfied with? What would that be?
That's really hard to say. Unfortunately, I feel like I'm a brick builder where I try to advance knowledge best as I can. But if I was to tell you that's something that I was most proud of, it's not actually an individual paper. I feel like everybody that I work with, we were able to figure out, or I guess to students and residents and fellows, I believe I taught them how to critically think and break things down and apply classical mechanics, not those mathematical equations and so forth, but how to think from a basic, real basic perspective. For example, in shoulder, first thing to do is we need to break down different stabilizing systems. One is bony tissues, the other is passive soft tissues, and third is muscles. And by teaching the ability to break those 3 components down and build them back up, I think that probably is the most powerful way of analyzing any joints, including injuries and developing repair strategies. One more thing is also how to do research that most people don't understand, that most of the work goes on in the front end. Every single project that we published, we did not start our experiment until 50% of the work spectrum was already passed. So we put a lot of work in the front end, and then your experiment goes smoothly and your questions and answers are very clear. So I think fundamentals of mechanics and also how to do research, I think teaching those 2 things, I believe, in my opinion, was the greatest contribution to people in our field.
I'll make a point there to pick up on what Thay said. I think he makes a very good point that, sometimes you're asked to pick your single one paper or something, but really it's an iterative process. The first one paper builds on another, which leads to another, which leads to another. And there's, when you look back on it, it may seem like it's all these great accomplishments, but the reality is it's small little pieces. It's an iterative process there. And as Thay mentioned, it's more important you develop the techniques, the methodology, the approach, and that's how you be successful over the long term. And again, back to my earlier comments about identifying the area and sticking to it and focusing on an area, that's how I think you can really move the needle. Pick 1 or 2 areas, kind of focus on those areas, get a passion for it, and say, I'm going to spend the next 40 years researching that. Really.
Yeah, I'd like that. Maybe I can add one more thing to that. This is a podcast. Hopefully, a lot of the young people are listening. It's great to do research, and it's fun, and it answers questions that get you on the podium. But eventually, you should pick an area or topic that you're really interested in, focus in that, and that way you get much more gratification out, and you also end up making a much more significant contribution to the field approaching it that way rather than dabbling on 10 different topics.
I love, Ty, also that you referenced how you felt like one of your important contributions was all the things you taught to all of the people who had come to work with in your lab. I think that's so often overlooked by researchers, is the influence they have, not just on the field, but also on, the people that they train. Scott, I wanted to ask you, one of the things you've been really successful at is building collaborations with basic scientists. I mean, you mentioned earlier Dr. Anosky, and, the work that he did with Warren and how that kind of first sparked your interest. How, you've been really successful at building these collaborations. How have you built and maintained these collaborations, and what has it taught you about managing teams generally?
Yeah, great point. That's almost goes back to my earlier comment about research being an iterative process that takes time. So collaborations are critical, and no more so than now as the science and techniques become more advanced. As I mentioned, we've moved in toward using mirroring models now and transgenic animals, the ability to do RNA sequencing and flow cytometry and some of these powerful techniques where you need the scientific expertise. No one individual, especially as a clinician, has all the expertise. So it takes time, and it probably took me and still takes probably 8 to 10 years to really build up this team of individuals, scientific collaborators, technical collaborators here within HSS, and I've actually reached out and began working as an example of where you can develop collaboration. I've worked much more in recent years with our rheumatologists and immunologists. So we study inflammation and the role of inflammatory mediators and immune cells and tissue healing. Well, we've got these rheumatologists and immunologists here who are experts in that area. Those aren't individuals who orthopedists have typically collaborated with, but I've learned more from them than almost anyone. Then you reach out to other individuals in your institution and in your community on the scientific side. So yeah, it is really, really the most important part of, I think, developing a lab. And then you need to sort of nurture that. Once you've got a team of people, you have to be dedicated. You can't. You've got to show up for meetings. You've got to nurture it. You've got to be there. You can't disappear for days and weeks at a time. So, and that goes back to do that, you need to have a passion. Ultimately, to do this and do it well and make it fun, have a passion. Ty just mentioned picking a couple areas and really focusing on it. To do that well, you'll be much happier doing it and able to do it if you have a passion for an area versus, this is just I got to do is pay, study so I can get on the podium. Yeah, that's fine, but you're doing it because you have a passion for it. Have a real curiosity for your field, and especially on the clinician side. My goal is to translate what we do in the laboratory to patients. So at the end of the day, the goal is to not just learn intellectually about these two things, which frankly to me is fascinating by itself, but okay, how can I use that information to make my patients better? And that's, the translational part that we as clinician scientists should aim for.
Now, Ty, you and your colleagues have done a lot of really important biomechanics work, and you talked about your background as a mechanical engineer. A lot of our listeners, as it sounds like are people that are in their training. They're medical students, residents, maybe people early on in their practice. Tell us on why biomechanics is important for clinical orthopedics. Sell this genre of orthopedic research. Why, if someone's deciding what kind of research to do, why is biomechanics the thing that we should be doing?
I guess I have one-liner answer for that. One-liner answer is that I see orthopedic surgeons as engineers in medicine. That's why I think biomechanics is important. And everything is related to mechanical demands, and your body has to go along with it. And plus, it's fun. And from an engineering perspective, we look at things as initial and boundary conditions. From an orthopedic perspective, that becomes human anatomy and functional demands. So there's a lot of parallel way of thinking between biomechanics and orthopedic surgery. Now, the important part, I want to touch a little bit on what Scott was saying about residents and fellows and younger people wanting to do research and so forth. I mean, obviously, you got to have passion. But I think one of the biggest mistakes that young orthopedic surgeons make and also young scientists make is, well, this is my field and I'm going to study. I'm really good at it. So I'm going to do my part and then hand over the clinical part to surgeons. But that doesn't quite work. I mean, that is your fundamental responsibility. But if you're a scientist or an engineer, you have to make an effort to understand problems that orthopedic surgeons see, and try to stay up with the literature and be aware of what's going on clinically. And same thing goes for orthopedic surgeons working with scientists. They may not get everything, but they need to make an effort trying to understand what we're trying to do, because we don't want to end up answering a question that's not relevant either. And it goes the other way also. And so my thought with respect to that is you need to make an effort trying to understand what your collaborators are doing, and also have a real passion, like Scott's saying. There's no other real magic to it. It's for me, it's like nothing I'd rather do. Even when I retire, I may cut back on some hours, but I think I'm going to be doing this forever. So.
Yeah, I don't see it as a job. I see it as what I do. I love it. It's not, it shouldn't be, pick an area that you can have a passion for. It can be clinical research. It can be, biology-based, mechanics-based. Pick something. Doesn't matter what it is, as long as it is. By that, I mean, pick an area and develop that passion. Because then it's not a job. Then it's fun. It's what you do. It makes it easier to spend what, frankly, you have to do, which is sometimes nights and weekends. I mean, that's just the reality. It's the world we live in. And it's easy to do that if you enjoy what you're doing.
I think, go ahead.
Yeah, I wanted to answer Peter's question. I didn't quite answer his question. Why is biomechanics important? Because in order for orthopedic surgeons to understand how joints and musculoskeletal systems work, you have to understand biomechanics. That's why it's important.
There, as a surgeon, we know that. That's for sure, right? I mean, surgery is a lot of mechanics, and it's anatomy and mechanics. It kind of starts there.
Well, let's move that on to a different aspect of research that's so clinically relevant and has become such a hot topic in the last few years. And Scott, we'll go to you because a lot of your work has recently focused on the topic of biologics and cellular therapy, stem cells, PRP. Is any of this really ready for clinical use right now? And what does the next 5 years in this field look like, both from a clinical perspective as well as a basic science perspective? That's a loaded question, so take your time.
Yeah, well, it's an area that has great potential, obviously. Honestly, I think that what maybe arthroplasty was to our field in the 70s, regenerative medicine or biologics, if you will, can be in this next decade. Are we there? No. I would submit to you that much of this is in its infancy. There are some, techniques and there are some applications that have some data, now, obviously PRP and things like that, but really we're just scratching the surface. So I would submit to you that on one hand, the field is very young in its infancy. On the other hand, there's tremendous potential. Needs further development. As you know, we've all seen it's an area that has, frankly, a lot of indiscriminate use. It's aggressive marketing. And those of us that work in soft tissue see the attraction of biologics. You have patients with difficult problems, meniscus injury, tendon injury, cartilage injury, where we, frankly, don't have great solutions. They see then on their side the appeal and attraction of stem cells seems sexy, seems fancy, seems cutting edge. It's a perfect storm where you have this patient with a difficult problem. We don't have great solutions. Patient sees these attractive techniques are out there, and that's so it's on us to evaluate these treatments in a much more rigorous fashion. What led me to really start our regenerative medicine effort at Special Surgery was, as I'm sure you do, Rachel, you see patients all the time who ask about, stem cells, this, that, and the other, and you try to educate them, and they say, no, Dr. Frank, you don't understand. Dr. Smith down the hall he's going to cure my arthritis with stem cells. And you could try to educate the patient. But the reality is, they're going to go down the hall and see someone else, or in New York, they're going to go down to, 4 other institutions. So I said, let's keep these patients here, do these treatments if individuals want to do some of them, but let's do it in a rigorous fashion. Put these patients in a clinical registry. Obtain a biospecimen that we can look at in the laboratory so we can evaluate composition, biologic activity. Let's do this in a rigorous fashion to move this field forward. And I think that's what we need in this area. Don't throw out the baby with the bathwater, because what's going to happen is if these techniques are used willy-nilly and indiscriminately, the data will be as it is, kind of variable. And people say, this stuff doesn't work, and they'll move on. Well, that's not the case at all. Clearly, this needs further development. I think it's on us to, as clinician scientists, to design the studies both in the laboratory and then link that with our clinical studies move the field forward. So that's an area that, it's a driving passion for me because it's something I see on a regular basis with our patients. I see with our athletes all the time. And I think we can really make a contribution to her, Rachel, in the next, 3, 5, 7 years. It's not going to be a year or two. It's going to be a longer-term prospect, but an area that has tremendous potential.
Scott, I wanted to follow up with you about that. I think, first off, great kudos to you for doing this work. And I think I see the same pressures I'm sure you see from patients to move this forward and to try and get it ready for clinical use. One of the major limitations on stem cell research in this country currently is there are restrictions on modification of stem cells and then reimplantation of them that are not present currently in other countries. And certainly I've heard patients say that to me, well, I need to go to Thailand to get this done because they can really do this and you just can't do this in this country. Respond to that. Do you think that's true? Do you think we understand how to do that at this point anyway? Or does something need to change from a regulatory perspective before we're really going to be able to move that forward?
Yeah, even if we change a regulatory environment where we could do ex vivo, quote unquote, manipulation, right, of a bone marrow aspirate or an adipose cell formulation, Peter, we have a long way to go before we're there because we need to understand what are the particular cell types that we want to isolate. What we need to match the treatment to the underlying pathology. The reality is the number of true stem cells by any formal cellular or molecular criteria in any of these formulations is vanishingly small. And then you expand that. So, in fact, a true stem cell is probably the least prevalent cell in any of these formulations. Now you expand that in culture, and those cells become even less prevalent. And in fact, there may be cells in a formulation that compete with or inhibit the desired cell. So again, we need much, much more information. Even if you told me tomorrow I could take, a bone marrow aspirate to the laboratory and do some type of cell sorting and culture expansion, I think we're a long way from knowing what type of cells do we want to sort for, how do we want to isolate those cells, what cells do we want to expand, and frankly, it's probably different for each different condition. So ultimately, a precision medicine approach is going to be required where we need to identify not just what we're putting in the patient, but also what is the patient's pathology, and ultimately match the two. We put the same PRP or BMEC, if you will, in for cartilage, for tendon, for ligament, for muscle. Well, that doesn't make any sense, right? These are all very different tissues and different pathologies. And so we are, again, I think that's why I say this field, I think, is in its infancy. And so patients that go, medical tourism, we all see it. There are other countries obviously have the ability to do some culture expansion and things like that, but boy, there's still a lot we don't know. And some of those places, you don't really know what's being done. The regulatory environment is more lax, so I often warn patients, listen, buyer beware. It's hard to really, they ask you to evaluate these techniques. Hard to do that because there's very little rigorous information and often out there to really guide us in guiding our patients. So again, back to what we need to do to define the major burning questions and then start to answer them in a collaborative way here.
I think that's such an interesting point that certainly the approach is going to be different for tendon and cartilage, and certainly I'm certainly seeing that indiscriminate approach, but by those that are champions of this currently. Let me ask you this: so, I know you've been working on this, which is which stem cells do we need in which injuries, and how do we activate them? How do we isolate them? What are the next steps? Like if you have your crystal ball, and you're looking into the future of let's just give an example of a rotator cuff tear.
Mm-hmm.
Like, what do you think is the next biologic to come on the market, or the next biologic that we can actually use clinically in that setting?
I think it will be using cells, but I think it will be a different approach here. I think it will be understanding that cells are producing a number of signaling molecules. I think where the field is headed will be a couple areas. One is we'll learn how to stimulate the intrinsic progenitor cells that are present in many tissues. Cells line the walls of blood vessels, pericytes, and cells like that are inherent or resident in many tissues. There are these in connective tissue progenitor cells that are in fact present. Question is, how do we leverage those cells? Well, I think that we can do that through biologics, whether that's a cytokine, whether that's something derived from autologous blood, or whether it's a population of cells that we inject that produce the signaling molecules that mobilize or stimulate those intrinsic progenitor cells. So I think that's one area. I think the other area where we move forward is understanding the fundamental and critically important role of immune cells and immune cell subtypes and their interaction with progenitor cells. I mean, think about tissue injury. Surgery is injury. An injured tissue there is a very complex and evolving inflammatory milieu in that tissue. And each tissue may be different, various immune cell subtypes and complex mediators that are present. I think it's those aspects that initiate and regulate the healing process, and frankly probably regulate those intrinsic cells that are present in tissues. I think we'll learn a lot by actually working with our colleagues that understand basic aspects of immune function and inflammation at a much more robust or detailed level.
I'd like to add a couple of comments to that. It kind of follows up on biomechanics part. What Scott's been saying with the stem cells and biologics, I think mechanics also play a big role in biologics, because you have to figure out how to deliver it, and you have to create a mechanical environment that cells will react to, and you have to have whatever for the biologic that you deliver to stay there. And most importantly, you have to have the host conditions that is ideal, or that is receptive to the biologic treatment that's going on. So in some ways, like, to simplify it, I kind of look at all this as we're building a house and we have all these fancy house parts that we're trying to figure out, which are all these different cells, and trying to grow the right type of tissue. And then we have to get it to the place, and we have to know how to build our house. And then we also have to make sure the foundation has to be strong, which will be the host environment. So it's a very exciting research. Like Scott was saying, it's early stages, but I think there's a lot more to come, and a lot of people working on different aspects, and truly exciting part, because I think that's the future, merging structure integrity with biology.
I'd pick up on that, Ty. It's a great point. I'd pick up further to say exactly, Rachel and Peter, most of the vast majority of work in this whole area of biologics is on the biology side. Clearly, mechanical loading affects the biology in a most fundamental way in all of these tissues. We're dealing with musculoskeletal tissues, see mechanical load, compression, shear, tension. This isn't a liver or a kidney. And so Ty brings up a really important point, the interaction between mechanics and how that affects the biology. And that's been an interest of ours for several decades, honestly, understanding how mechanical loading affects the biologic events. And so great point. And it goes back to, again, collaboration. So back to how do you do good research? Well, it's interdisciplinary or multidisciplinary, and you go back to collaborations. You need your biologists, you need your engineers, and you need that paired with your clinicians. And only then can you move the field forward.
Well, it's amazing because that marriage of mechanics and biology has really driven innovation from an orthopedic perspective over the last decade, if not longer than that. And one of those innovative areas is that with treating the irreparable rotator cuff. And Ty, a lot of your work has focused on this, quite recently with superior capsular reconstruction and repair and reconstruction of irreparable rotator cuffs. So tell us a little bit more about your work in this area, and where are we going in the next 5-10 years? Because the innovation, with rotator cuff treatment across a wide spectrum of different options, ranging from SCR to repair with augment to biologics to the balloon, et cetera. There's so many different options. Where are we going in the next 5 to 10 years with the cuff? And what can your work help us, discover in the future?
I think it's starting to mature and expand at the same time. The superior capsular reconstruction itself is, I think, maturing. So that procedure is going to stay and just get refined. But the same concept is going to expand like crazy, like balloons and biceps and tuberoplasties and what have you. And all those things came from a concept that when you look at irreparable rotator cuff tears, it's rotator cuff tear plus the superior capsule, which is a passive restraint system. So what we've been really understanding throughout past 10 years, I guess it's been about 10 years. It takes a long time for a message to get out there, because now I think people are starting to understand these different stabilizing mechanisms there, how that is being applied. So one of the things that came out of superior capsular construction is that the graft that we use that has to keep the humeral head down as a passive restraint system. And now that also has to work in a cuff deficient environment. So that's why Dr. Mihara's graft kept on getting thicker throughout the years. The reason for it getting thicker is as you increase the thickness of the graft, you decrease the tensile demands of the superior capsule or the graft that you have. So there's give or take, and you have to understand that balance depending on what graft choice you're using. Because at the end of the day, no matter what procedure you do, you still have a cuff deficient shoulder that has to work. So you cannot be reconstructing the superior capsule itself. So this is, I'm talking about massive irreparable rotator cuff tears, that those ones that you may not even do a partial repair. But if you can do a partial repair, I think that you have to assess the patient's demands very carefully. And if their demands aren't so high, probably partial repair with some type of augmentation will do just fine. You don't have to go through the entire superior capsular reconstruction process. So that augmentation again becomes, or it's also wide open with the biceps or with patches or with the balloon. I think the whole purpose of the balloon itself is, the concept again is very good because you're depressing the humeral head from a mechanical perspective. But at the same time, what happens when the balloon disappears, resorbs? That's a part. That's a question that has to be answered. I think it's a very easy procedure. You depress the humeral head, but you don't really stabilize the glenohumeral joint like superior capsular reconstruction does. So I think it relieves pain, but balloons movement, somebody will have to look at some follow-up to really look at what's happening. And then why are these patients actually better even after the balloon pops? The same question is raised with Dr. Mihara's patients, where his results are far superior than the dermal graft SCR procedures. And when you look at that, aside from it being an autograft, there really isn't that much difference, except fascial autograft being really thicker. So that still has to be teased out. I just gave a talk to shoulder and elbow on the kinematic changes, that it is clearly, it is very clear that superior capsular reconstruction procedure stabilizes the joint, but the kinematics is significantly altered. But that's not necessarily a bad thing, because it has to function in a cuff deficient shoulder. So to answer the question, I think the field is wide open because people are trying all different things, just trying to depress the humeral head to let the deltoid work. Or a secondary thing is just augment the repair so a patient will be pain-free and they can function to their level of mechanical demands. So as far as creativity and the concept being expanding, I think it's going to continue to expand. Superior capsular reconstruction procedure itself, I think it's just going to get refined and hopefully make it a little easier. So it'll be easier for average orthopedic surgeon to use. So I know I rambled a bit, but I think the procedure itself is mature. The concept will continue to expand because people are going to figure out different way to depress the humeral head.
I wanted to follow up with you about this because I think this particular topic is one that's of interest to a lot of surgeons right now. And as you mentioned, it's a solution for a difficult clinical problem, the irreparable rotator cuff tear, the cuff deficient shoulder that, as you mentioned, disrupts the biomechanics of the function of the deltoid and the remaining cuff. You talked a lot about bringing the head down and how that restores the normal center of rotation. There's been some recent clinical studies about that as well. There's a biplane fluoroscopy study that was just published, and then there's also a paper that was presented at ASES that's kind of a serial fluoroscopy study with the arm raised that challenges some of those questions and suggests maybe that the SCR functions more as an interposition arthroplasty at the acromial humeral. articulation. Tell us about that. You've done a ton of work looking at this biomechanically. Do you think that effect is more important? Do you think that there's the fact that it restrains superior migration is important, or are those two effects really one and the same?
Those two effects, I think there's a lot of things going on. I think if you look at it from real basic perspective, it's depressing the humeral head and centering the humeral head so deltoid can work. But is it really that effective for initiating shoulder abduction? It probably is not. There's other type of adaptation that's going on. But one thing to think about interposition arthroplasty versus superior capsular reconstruction is if you take that joint through rotational range of motion, the restraint provided by that capsule or that passive soft tissue is gone. So I think at certain rotations that you look at the patient or the follow-up that you do, at certain positions, that is true. It's interposition arthroplasty. It's going to work exactly the same. But if you take it to different range of rotation and try to perform the same task, you're going to see a huge difference. That's why we're actually looking into kinematics of irreparable rotated cuff tears more before and after superior capsular reconstruction, and for that matter, for other augmentation procedure as well, because that tension or tensile function of the superior capsule or any glenohumeral joint capsule plays a big role, especially in extreme rotational range of motion positions. Did I answer the question? I hope I did.
You did. It was great. Scott, your area, I know your research is in a very different area, but I wanted to ask you, with all the research you've done about tendon healing, what is your thought here on an acellular dermal allograft? Do you think, based on what you've known, that can become kind of a pseudo tendon or pseudo ligament with time? Tell us what you think.
I think it can. I think we need to encourage, clearly, at the end of the day, to heal tissues and to repair microscopic damage. What do we need? We need cells. So that material needs to be repopulated with cells, whether that's done ex vivo prior to implantation or more practically and realistically, how do we encourage cells to repopulate this material after surgery? So to that end, I think we're going to learn how to put the appropriate signaling molecules and stimuli in that material. And that may not be just chemicals like cytokines, but also stimuli based on the microstructure of the material, the chemistry of the material. So the composition and microstructure, in addition to any exogenous small peptides or cytokines we put in. But I think some way to modify the material so that we are attracting cells into the material. And then how do we differentiate those cells into the desired cell phenotype, into a tendon-like cell that synthesizes the appropriate matrix proteins? That'll be where the challenge is.
So I think one more thing to add about that superior capsular reconstruction is you're doing that with the dermal graft or fascial allograft or what have you, but it has to actually replace the function of the superior capsule, supraspinatus, and the bursa, all three of them. So it can't be just one single reconstruction. And with the dermal graft, there are some cases that people are showing that dermal graft actually thickening, but eventually, I think all these procedures need the volume as well as remodeling.
Scott, you've been really successful, obviously, in basic science research as a clinician. Many of our listeners are trainees and surgeons early in their practice. Tell us, what advice do you have for someone, say, in residency or in fellowship, or even early on in their career, if they're inclined to be an academic, surgeon scientist, but maybe don't have the resources of HSS or University of Utah or University of Colorado, or maybe they do, but perhaps they don't, or they're in private practice. How can they get involved as a surgeon scientist at an early phase in their career?
Establish collaborations. I think the most successful way to do this is we all have seen and learned is a surgeon, a clinician collaborating with the basic scientist. That scientist can be in the biology side, mechanics, or something else. I think ultimately seek out scientists with whom you can work. And it may take you a year or two or three or five. Look out, find people in your institution And then at the same time, you do need institutional support. So in an individual who really wants to pursue this pathway, you talk to your chairman. You need to help them understand the importance of this, and a good chairman at a big department will. That it's, and frankly, early on, and honestly, it costs money. It costs them money, but it comes back to institution 10 different ways. And the research that you develop, in the visibility for the program, and attracting the kind of people you want there, as far as residents, as far as fellows, putting people on the podium, things like that. It makes everybody better. And so, but it's an investment, human resources and financial resources to do it. But the simple answer to your real question is establish collaborations. That's your best way to start, because again, it's hard to go and start doing real basic biology or mechanics research all by yourself. As the techniques become more and more involved and more technical, you need those collaborations.
Thay, let me ask you, oftentimes basic science comes, at least basic science research, comes under attack by pure clinical colleagues as not being clinically relevant. We see this at meetings from time to time. We also see it more commonly now in 2021 and moving into 2022 on social media, on Twitter, on LinkedIn, et cetera, where there's maybe too little fidelity between the experimental model and the in vivo clinical situation, and so-called clinicians who don't do any research may question clinical applicability, state that there's no ability to draw conclusions from data. This is cadaveric data. This is lab data. This is not real time. It's not applicable. Defend basic science research for all of us. Tell us, why is this important, and why do we need to rely on these studies to drive our clinical decisions?
Well, I think basic science is critically important because it provides understanding for what we see. I think one of the things, this may be, I'm trying to get my thoughts together. One of the things about our field or medicine is it's still largely apprenticeship, where certain things happen and surgeons do, or physicians do, and they treat it the same way as someone else saw it before. So it's largely an apprenticeship in many ways still. But what science does is that it gives you the fundamental understanding of the mechanisms that are involved in either injury or healing. And what experiments do is that experiments explains, or the scientific studies explains, certain cause and effect phenomenon in every pathology. So when somebody says certain studies are not clinically relevant, they may not have a direct clinical relevance, but it has to go through that spectrum of, from fundamental basic question, which would be totally irrelevant, but totally mechanism based. And then it goes through a series of experiments to the clinical setting. So in order to treat effectively and also understand the pathology, you have to understand the mechanism. I think that's where the science comes in. So sorry, I was rambling a bit, but I think science comes in trying to explain or provides understanding for the mechanism, whether it be biology or mechanics.
Scott, I want to ask you a similar question, but in a different way. Recently, a lot of clinical studies have made headlines in the main press or the lay press. A few come to mind in terms of from now several years ago, the sham surgery versus meniscectomy, and more recently, PRP having no effect for arthritis and other pathologies, where the headline is grabbed, it goes into mainstream media, and everyone's talking about it. And it's basically based on one sentence in an abstract without reading any of the data that went into that study. How do we as clinicians use those types of studies or look at those types of headlines and explain that to our patients? How do we take that type of research that might get spun in a way that doesn't represent what the actual data is, and talk to our patients and even talk to our colleagues about what those studies actually mean?
Yeah, I mean, I think first, know the field, have some expertise in a given area, so you have a much broader view than one or two or three studies. If you've read the literature for over some years, any study that, you can go today, obviously, right, and find 5 studies to support any view you want. So the way you really, I think, can have a more nuanced understanding is knowing the literature, over time. So by reading, and at the end of the day, quite simply, you read, and then you read some more, and after that, you read some more. That's the only way you get good at the field. So, but point is, I think knowing the field so you can interpret that data, and then you read those papers carefully. Yeah, we're all many people are prone to sound bites. They read the abstract at most, and they read or just the conclusion of the abstract. Well, obviously that's very, very limited. I think it's on us to be able to understand the paper and interpret that for our patients, because that it gets picked up by CNN or something, and you see it's a sound bite. All you can do is do your homework, study that paper, and know the field. And that's the best way to try to educate our patients and our colleagues, frankly, too. And that helps you also all studies have even a kernel of truth, and they all have flaws. Even the best studies have flaws, but each one has a kernel of truth. And again, research is iterative, so you can learn a little bit from each study and use that to say, okay, I'm going to use this to design my next study. What are the outstanding questions raised by this study? How does that fit into the overall field? Where this field is in 2021. How does this one particular study add to it? What questions does it bring up? And that can help you, move forward with your own research agenda. So, no paper is perfect. They all have some value. They all have some limitations. And as you know the field, you can help you to pick out what is the value, what is limitations, what is what is really not worthwhile in a paper, and conversely, where does the paper make a real contribution?
I think, Rachel, you bring up a really important point, and I personally avoid the media at all costs because they always seem to misinterpret something. But I think us as educators, we can actually do a lot for our students, residents, and fellows. That's one thing I've always emphasized on, is that we're so used to instant answers and short, summarized results. And that's through education. I think we need to really teach people to read the original work, cite it properly, and understand the strength of limitations of whatever papers they're reading, instead of having somebody interpret it for you. So I think if we want our field to really not get hammered by these media people, we need to educate our people best as we can, so they can stand up and correct things if need be. So I think that education is, in some ways, it's like trying to swim uphill, but at the same time, we've got to give it our best effort to young kids, because they have everything on their phone, and nobody reads full papers. So when I hold journal clubs, I make them go through the entire paper, even though it takes a lot of time. Just make sure that there are a lot of important things in there that they're missing out.
I was thinking as you were commenting. Oh yeah, go ahead, Scott.
Just a quick comment. You say you get what you give. Or another thing I like to tell our trainees is nothing hard is ever easy. And the point there is, as Thay said, you can do it the easy way. You can read, a 3-sentence summary and not learn much, or you can put the effort in and learn something. Pretty simple, right? I mean, put the effort in, you'll do a better job. But yeah, it's hard. Hard work is hard. That's what it takes, though.
Yeah, simply put.
Yeah, I was just thinking as you both were speaking, it is a good testament to why the art of going through journal club is so important, even as a student or as a junior resident, when you're post-call and tired and you don't really want to go through, all the metrics and regimen that you have to do when you do a good journal club. It's so important to learn how to critically read an article, so that even if you become a pure clinician and never do a research paper in your career, you at least know or had a foundation for how to interpret literature, and hopefully can rely back on that. Just so critical. For both of you guys, we're kind of getting to the end of our time here, but I do have one question for each of you, and we'll start with Thay first. In the next 5 to 10 years, what is the hottest topic in orthopedic research?
Wow. Well, I'm biased. I'm totally biased because I'm an engineer, and so I think with all the advances in technology, I think the patient-specific treatment from implant perspective, I think, will be a big thing, because the imaging is getting better, 3D printing is getting better. So any type of reconstruction, I think, it's going to go through more of the more of more of the intelligent process and be able to manufacture or treat and manufacture patient-specific devices for a lot of things. So from engineering perspective, that's what I see.
And Scott, how about you? From our what are your thoughts from the West Coast?
So we all have our
patient-specific
biases,
devices.
and actually here's an area where Ty and I overlap pretty well. I think so. Clearly, we have our own interests and biases, and but I think in where this field's going and where we'll make progress is in a precision medicine approach. That's kind of what Ty just said. Kind of matching. I think, and then I can go back on the biology side and mention on the biologics here, matching the particular biologic agent, cytokine, growth factor, cells, whatever you want to use, to the patient's pathology. I think right now we are, it's a crude approach. We use the same formulation for the same pathology. Well, you take 10 patients with arthritis, they all have a different condition, biologically, at the cellular or molecular level. What we call arthritis is probably 25 different conditions. We need to, as we learn how to phenotype our patients, then we can match the treatment to that patient. This precision medicine approach is obviously huge in all areas of medicine. I think in our field will really play an important role. So on the mechanic side, Titus mentioned your precision implants and specific implants for a patient. I think we'll do the same specific for a precision biologic implant for the patient. So I think we have a lot of parallels right there.
So I think to summarize that, there's a line I usually say is that human beings haven't been around forever, and not much has changed in our body or with respect to our body, but technology certainly has changed. So if you look in the literature, every problem that we see, somebody's written about it, but we just didn't have means to solve it. And I think as technology advances, we're able to solve these things by applying these things.
Well, I wanted to thank both of you for coming on. It's very generous of you to share all of your insights, and you guys we covered a huge amount of ground. So it's really a testament to both of your years of expertise and experience in the field. This is about all the time we have for this podcast. For all of our Shoulder Nebel listeners out there, don't forget to subscribe, and we will see you next time.